Okay, so welcome back everyone. Today we're talking about divide and conquer algorithms. Here's a quick introduction, okay? All the material is covered in the book chapter, so you can follow there as well. But the divide and conquer algorithm design technique, it's a design technique to solve complex problems by breaking into smaller instances of the same problem, and then combine those results after we have those mini results. It's a recursive methodology, and we will be applying the programming technique of recursion usually. It has those two typically used accompaniments. We'll be using principle of mathematical induction, PMI for short, to prove the correctness of our algorithms at times, and we will be using the recurrence relation solving for computing the time and the space complexity as needed. So here we're talking about divide and conquer, the computer science version, not the management version. In management also sometimes we use the term divide and conquer, but there usually sometimes we are saying divide and conquer by dividing the problem into different kinds of subproblems. But here when we say in the computer science context, it's a pretty formal methodology where the subproblems must be of the same type. Okay. And as recursion, as you're familiar with recursion, a recursive program is an algorithm that calls itself on smaller input. An example of that is a sort algorithm, which we'll see a little bit later as well. So you sort and you sort some portion of the same array as well by using a recursive mindset here, like you do here. Now, typically, recursive program will also have, while it's not shown here for detail, but it will also have a base case. So where you see that if the input is of a small enough size, you solve that particular problem instance separately. So what is the difference between recursion and divide and conquer? Recursion is a programming technique. Divide and conquer is an algorithm design technique. They are fairly related, but strictly speaking, you can have a divide and conquer program that does not apply recursion, rather it uses iteration. So it's certainly possible, but they are still fairly related. So when we talk about the divide and conquer algorithms, there's a generalization step that sometimes is a little bit difficult to master. But in the generalization step is a step in which we make the problem a little bit more general or a little bit more complicated in order to be able to solve the bigger problem. So this is called the generalization step. So it's a little counterintuitive that making the problem can actually help us in solving it. But the intuition for why that's the case maybe can come from the fact that because you're going to be applying recursion, if you make the problem harder in your recursion step, you are going to be able to expect more things from the sub solution. So that's where the generalization step can come in, and we'll probably see that in some of the examples of the divide and conquer algorithm design technique overall. So here's a general template of a divide and conquer program, not talking about any specific problem, but just speaking about what a general template of the solution will generally look like. So again, you'll have a base case where you'll say if the size of the input, that's j, is small enough, just solve it directly. That could be a brute force solution or something which will be applicable for when the input size is small. Otherwise, you divide the input into one or more parts, that's j1, j2, etc. And then you make those recursive calls. So then here you can see that divide and conquer, divide and underscore conquer method is being called on the smaller inputs, the same method that we are in. That's of course recursion. And then you have the merge step. So you're merging all of those sub-solutions that you got in the recursive calls S1, S2 into a global solution, and then you return that. That's a general template. If we look at this general template from a time complexity perspective, then we can see we want to come up with a time complexity of this overall algorithm. And let's suppose the size of the input is n, then we want to call it T of n. So in T of n, we will say there is some time that you're checking in this if condition. Then you have a divide step. Then you have the recursive calls, and then you have the merge step. So you can write your overall time complexity as T of n is equal to A times T of n by B plus F of n. Okay, let's look at this part again. T of n is what we usually call the time complexity of the overall algorithm when we are putting it in terms of variables. So we're calling it T of n, where n is the size of the input j. So we do certain things here that which are non-recursive, and we can simply add all of them up here, and we call that to be f of n. We don't know what f of n is in this general template, but when we are solving a specific divide and conquer algorithm, we will be able to compute it by looking at these steps specifically. And then here we will have the recursive calls, where the recursive call, there could be 2 recursive calls or 3 or 1, more than 3 as well. So the number of recursive calls we're calling is A. So there are A recursive calls. Now each recursive call can be of a size smaller than n. Let's suppose it's of size n by b. So that means the input size becomes b times smaller. As a very trivial example, you can say maybe you're making 2 recursive calls on half the problem size. So in which case A could be 2, B could be 2. But again, in a general case, it is possible. It's something else. So you could write T of n is equal to A times T of n by B plus F of n. It is possible these recursive calls are not of the same size maybe, and they're not of a fraction. Maybe this is size n1, this is n2. So you may have to write T of n is equal to T of n1 plus T of n2 plus T of n3 plus however many recursive calls you have plus F of n. But if you see that you're making A recursive calls all of the size n by b, you can also shorten that to be AT n by b if that helps you. So this is a general view of the time from a time complexity perspective of a generalized divide and conquer algorithm. When we look at specific, we will not need to worry about f of n, rather we'll have those specific scenarios there. There are many example algorithms for divide and conquer, binary search, merge sort, etc. Closest pair points. There are separate videos for those. But here, let's take in, for the purpose of introduction, very simple example of merge sort. Merge sort is a quintessential divide and conquer algorithm where we are given an array and we just want to sort it. We can say we want to sort the entire array or between the bounds, whichever way your use case will be written as. So because it's divide and conquer algorithm, we simply divide the array into 2 arrays, A1 and A2, and then we merge sort A1. That means it's that's your recursive call. Merge sort A2, that's your right hand side, another recursive call, and then you call the specific function that you will write separately, which is to merge 2 arrays into a single array, and that becomes your merge step. So overall, merge sort is written very easily, usually as this, and the merge 2 arrays is another separate function that maybe takes about few lines of code there. So the merge sort is a very easy recursive algorithm. It's a perfect example of a divide and conquer because it does those steps in the right sequence. It's easy to explain. Those two recursive calls, the divide calls, the 2 recursive calls, and then the conquer step here. So that's pretty much what we have from the purpose of the introductory videos. Look out for other videos to look for those topics in detail, such as how to solve recurrence relations, how to do the master theorem, closest pair of points, etc. That's all I have. Keep learning.